absorptive power, emissivity, etc. And we had seen about Stephen Boltzmann universal constant for radiation, right? And the relationship between the rate of emission as well as the rate of absorption with respect to temperature of the surface, etc., net rate of cooling, etc. So let's continue from that point onwards today. So in this section, we are discussing about heat transfer. So now we are absolutely at the end of the section of heat and thermodynamics. Okay, so the quick recap of concepts we had seen last time. Stephen's law of radiation. The emissive power is given by this relation, and the absorptive power is given by this relation, okay, where we have a surface at temperature T, okay, and suppose its surface area is S, whereas the surrounding is at temperature T0. So this is the surrounding temperature in kelvins again. Okay. So capital E gives us what is called the emissive power, where the name is misleading. It does not have the unit of power, but it is having the unit of power per unit area. So it's in watts per meter square. And E is the absorptive power. Again, in watts per meter square. And E for any material is equal to A. Emissivity is equal to absorptivity. So E for any material is E for that particular material with respect to E for a black body. At same temperature. So E is equal to 1 for a perfect black body. Whereas E will be between 0 and 1 for all known materials. Okay. It can be argued that E is nearly equal to 1 for a black hole, but here we are talking more about, materials which are more in context of heat and thermodynamics related systems on the surface of the Earth. Okay. We're not talking about an extreme situation of the phenomena of black hole, where because of infinite density and massive gravitational field, it has completely warped properties compared to normal matter. Okay. So in normal materials, there are substances like lamp black, etc., that come reasonably close to black bodies, in sense that their value of E might be about 0.94, 0.93, etc. But nothing which has E equal to 1 or even can be approximated as E equal to 1 in that sense. Okay. So then based on this, we had seen that if the temperature of a surface is greater than the temperature of the surrounding, then the net rate of heat loss we can say minus dq by dt net is equal to E sigma into surface area into temperature of the surface to the power 4 minus temperature of the surrounding to the power 4. And you can just say that vice versa of this equation is that if the temperature of the surrounding is greater than the temperature of the body, then there is a net rate of heat gain by radiation, and that is plus dq by dt net, which will be again E sigma S, but this time into T naught T to the power 4 minus T to the power 4. So this is what we have learned so far. Of course, these equations come because emissivity is equal to absorptivity for any material. So this is so far what we've learned, and I think we saw a couple of examples of the application of this in the last lecture. Now the thing is, at JEE Advanced level, there will be some types of questions where you have to apply the concepts of radiation as well as conduction in the same question. Okay, so there will be more than one phenomena happening as far as heat transfer is concerned, not just a single phenomena of radiation. So let's understand that first today, then we'll move on to Newton's law of cooling. So this up to this point is what we had done in the last lecture, so need not write down again. Let's start with an example. So in this example, what is happening is that we have, an insulated kind of system like this that consists of an insulated chamber, right? So there's an insulated chamber, but there is also say a metallic cylinder or rod kind of thing. It's placed like this, such that part of the metallic cylinder is exposed to the outside environment on this side, and the other face is inside the insulated container, and the insulation of the container is also continued, or there's also insulation, you can see, on the outer surface of this metallic rod, okay, but not at the open face on this side. Okay, so this side is an open face. So this is all insulation. Okay, so this part is all insulation. This is an insulated container. But this thing in between now, it's a metallic cylinder, a solid metallic cylinder. So the properties of the solid metallic cylinder given to us is that the thermal conductivity of the metal is 150 watts per meter Kelvin. The length of the rod is unknown. The cross-sectional area of the rod is 20 centimeters square. Okay, so this is length. This is cross-sectional area. Now this is the open face. Okay. Now inside this we have some kind of a heat source. And this is what is given to us. Now, given the heat source maintains the temperature inside the container at T1 equal to 500 Kelvin at steady state. Okay. And as a result, the open face of the metallic cylinder is at T2 equal to 400 Kelvin at steady state. Now the outside environmental, okay, or you can say atmospheric temperature is the normal room temperature of 300 Kelvin. Okay. So if the metal surface has emissivity equal to 0.5 and sigma's value is given to us approximately as 6 into 10 raised power minus 8 watts per meter square Kelvin to the power 4. As you know, that is the SI unit. Okay. So if these values are given to us, first of all, you have to explain why T2 is greater than T0, even in steady state condition. So of course, that's not the type of question you will get in JEE because you have to explain this over here. But anyhow, second, you have to find the length of the rod. That is the metallic cylinder. And third part, we have to find the rate or power at which the heat source generates heat. Okay. So just can you tell me briefly the answer for the first part? Can you tell me how come this is happening, that at steady state, the temperature of the open phase is not equal to the temperature of the surrounding environment? Or start by telling me how many phenomena are happening over here. What type of heat transfer phenomena are happening? What about the two ends of the rod or the metallic cylinder? They are at different temperatures now. So can anybody tell me the heat phenomena? Yeah. So that's correct, Nikita. Aman, that's correct. Okay. So both of you have understood, I hope, how it is possible that at steady state, the temperature of the open face of the rod, which is in contact with atmospheric air, is not at the same temperature as the air. It's at a higher temperature. How come that's happening?
Because from there, the heat is radiating out.
Yeah, so while heat is getting radiated, so as a result of that, the temperature will tend to decrease. But at the same time, heat is also coming into that phase now by conduction. Right?
Yes.
So at the right, I mean, if you look at the open phase, from one side, heat is coming into that side. That heat is conducting through like this in a heat current. And at the same time, that heat that is conducting through and is tending to make this surface rise in temperature. But it's also, there is a net rate of heat loss because of radiation. Okay, so the two have to balance each other. Okay, so the steady state condition here, this T2 equal to 400 Kelvin steady state, it means that the heat current, because of conduction coming into that open phase, must be balanced by the net rate of heat loss by radiation. Okay, so just apply that concept now and try to work out what will be the length of the rod. The inside is being maintained at a constant temperature of 500 Kelvin. That is what the heat source is doing by generating heat. Even though part of that heat, whatever heat is generating, it's is conducting through the rod, but it's continuously generating the same amount of heat as the rod is conducting. So as a result of that, the temperature of this phase will remain constant at T1. The temperature of this phase will remain constant at T2, equal to 400 Kelvin, okay, while the outside environmental temperature is 300 Kelvin. Rest all the required data is given to you. So just try this out. Okay, so anybody worked out the answer? So basically, see, what should happen is that for the rod or the metallic cylinder, this rate of heat current which is coming in should be equal to this net rate of heat loss. So this heat current should be equal to the net rate of heat loss due to radiation. At the open phase, whereas this is the rate of conduction, okay, across the length. Okay. So the length is some unknown L, thermal conductivity is given to me 150, area of cross section is given to me 20 centimeters square. Okay. This T1 on this side is given to me as 500 Kelvin. T2 on this surface is given as 400 Kelvin, and the surrounding temperature is 300 Kelvin. and also emissivity is 0.5, right? And sigma is 6 into 10 raised power minus 8, like this. Okay. Let's use all this information now. So this heat current will be equal to T1 minus T2 divided by thermal resistance, and that should be E into sigma into surface area into T2 to the power 4 minus T1 to, sorry, minus T0 to the power 4. Now in this surface area is the area A of cross section of the cylinder. Okay. Because this is the open surface which is exposed to the environment. Okay. Rest of the surface is of course insulated, so no heat is escaping from that. So this surface area will have the same value as the cross-sectional area on the left-hand side. So in fact, interestingly, to find out L, we don't even need the value of that. Okay. Ka by L into T1 minus T2 should be equal to E sigma into that same area into T2 to the power 4 minus T0 to the power 4. So as you can see, that area part gets cancelled out. We don't even need it. Okay. And from that, we should get K was how much? K was 150. Yeah, correct. So in SI unit 150 divided by length into 500 minus 400, that should be 0.5 into 6 into 10 raised power minus 8. That area has got cancelled out, and this is 400 to the power 4 minus 300 to the power 4. So this calculation just looks lengthy, it's nothing difficult. 150 by L into 10 raised power 2 on this side. Okay, that's 3 into 10 raised power minus 8 into, now we can write this as 4 to the power 4 minus 3 to the power 4 and take 100 to the power 4 common. So this will become 3 multiplied by 16 square minus 9 square. We can write it like this. Okay, into 10 raised power minus 8 into 10 raised power plus 8. So those two will neutralize each other. Okay, so we have 3 into 256 minus 81. And on this side, we have 150 into 10 raised power 2 divided by L. So from this, I should be getting L as 150 into 100 divided by 3 into 175, right? 50, 10. So I'm getting the answer as 200 and 200 by 7. You can just check. It's approximately the same. So this will be very close to 30 meters. Okay. So as you can see, we can even get the length, even if we did not know the area of cross section. The length that we are getting from this data is independent of how much the area of cross section is. Okay, that also means that if I replace this rod with a thinner rod, but with the same length, same thermal conductivity, same material basically, so same K and same emissivity, still at steady state, the temperature would have been same on the open surface, because that part is independent of area of cross section. But the second part is where area of cross section will come into play, because you want to find the rate at which the heat source is generating heat, or the power generated by the heat source. Okay, hope this is clear to all of you. Okay, Aditya, I'm explaining the first part again. So in case anyone has not understood the first part, let me explain. Just pay attention here. If you've understood, just continue working on the second part. So what is happening is now through this metallic cylinder, there is thermal conduction happening from left to right. Okay. And what is happening is that thermal conduction is happening because of a temperature difference which is maintained. Now, why is that temperature difference maintained? Because the heat engine inside the container is maintaining this side at a fixed temperature of 500 Kelvin. It's just generating enough heat to do that. That this temperature remains, this surface's temperature remains constant at 500 Kelvin. And the surrounding temperature outside is 300 Kelvin. So the moment this temperature differential is created, heat has a tendency to conduct like this. But as it has a tendency to conduct like this, the temperature of this surface has risen. So as it rises compared to the outside temperature, heat is also escaping because the rate of emission is more than the rate of absorption. So if this surface is at steady state, okay, that means T2 is constant at 400 Kelvin. It's constant with respect to time. So what that basically means, it means that the incoming heat by conduction, okay, at the open surface should exactly be balanced by the net rate of heat loss due to radiation. Okay. So this equation that I'm writing, this is at the open surface. Which is at T2 equal to 400 Kelvin. Okay, now so hope this point is clear now. This definition of steady state over here is clear now. Okay, so this quantity is equal to the heat current only, and this quantity is basically equal to the heat loss by emission minus the heat loss, I mean the heat gained by absorption. Okay, so that is your E into emissive power minus A into absorptive power. So it becomes E into sigma into surface area into T to the power 4, but in this case T2 to the power 4 minus T0 to the power. So in this definition, we are applying the concept that E is equal to E, and also that the surface area is equal to the cross-sectional area. So don't confuse this with here, which is the absorptive power. Okay, so let's write this as A0 so that we don't confuse the two. Okay. And so next step, this becomes T1 minus T2 upon thermal resistance. And then we substitute it. Okay. So there are two mechanisms by which heat transfer is happening: conduction across the length of the rod, okay, and radiation at the open surface of the rod. Now, actually, in this question, there is an assumption that we are making. And the assumption that we are making is that the primary mode of heat transfer between the open surface, okay, and the atmosphere outside is by radiation. Okay. In fact, not only it is primary, such that any convection that occurs is negligible. any convection is negligible. Okay, because in real life there will be some convection current set up over here, because air is also a fluid. Liquids and gases are both coming in the category of fluids. So air molecules also set up convection currents as they come in contact with the open surface, which is at higher temperature. And that also results in some net heat loss. But what we are assuming over here is that the radiation is the dominant factor. And compared to the dominant factor of radiation, we can neglect the effect of convection. So in case you were wondering about that, how we have not taken convection into the picture. So first of all, we cannot take convection into the picture because we don't know any formula, etc. related to that. It would become too complex. So in the absence of that, even if the question is not telling me to neglect convection, I have to assume that convection is negligible in this situation, because the information given can only be used to solve for radiation and conduction. Okay. So that obviously means the question is asking me to take into account that the convection should be ignored. So it's negligible. Okay. All right, anybody got the answer to the second part of the question? I'm just taking you back to the question. Rather the third part, but the first part was just theoretical. Anybody got the answer to this third part? So the rate at which the heat source is pumping heat is nothing but the rate of heat conduction itself, or that's equal to the net rate of heat loss by radiation. Okay, Aman, I will check your answer. So basically we've got all the ingredients required for that. We just need to multiply the right hand side of our earlier equation with the area of cross section. So that would give us the net rate of heat loss by radiation. Okay. Or we need to substitute the value of L in the left hand side and also substitute the value of area of cross section, 20 centimeters square. So don't forget to convert it to SI unit before substitution. Okay, so it's just calculation, nothing else, no other concept really. Okay, so the third part, the power generated by the heat source, that should be equal to the heat current, or that should be equal to the net rate of heat loss by radiation. Okay. So that's basically equal to, just write it like this, or okay. So whichever way you go by, so this would be 100 into 150 into 20 into 10 raised power minus 4, okay, divided by that whatever we had got. What's the value of length? Sorry, 28.57. Or that's the same thing as if I go by this, this is 3 into 20 into 10 raised power minus 4, okay, into 175, right? This much in watts. If I go with this, it is 3 into 10 divided by, okay. So let's see, these two should give us the same answer.
By 7. So we can write 28.57 is 200 by 7.
Yes, sir.
Okay, okay, okay. 200 by 7, right? We can write that easily. So this is 300 divided by 200 by 7. So 1.5 times, so this will be 10.5.
So 30 by 200. 30 by 200.
Oh, sorry, 30 by 200. 1.05 watts. Correct?
Yes, sir.
Yes.
Okay, or joules per second. Okay, and this should also give us the same when we calculate. Yeah, it is giving the same. All right, so that just verifies. So at the exam level, you just do whichever calculation is more convenient to work out, either this one or this one. So this is one common type of question at the JEE level, especially JEE Advanced. When the same question, you have to connect conduction and radiation both. Okay. Now, so this is clear, I hope. Okay, now next we move on to another important aspect of this. Okay, so if a situation like this happens, that if the temperature of the surface is equal to the temperature of the surrounding plus delta T, but such that delta T is small compared to T naught. Okay, so if surface temperature is larger than the surrounding temperature, but not by very much, then in that expression we can do a binomial approximation. Okay, or we can say that T minus T naught, okay, that difference is very small compared to T naught. But keep in mind over here that these should all be in kelvins. We should not do the comparison in degrees C. Okay. So for example, if I say the temperature of the surface is 27 degrees C and the temperature of the surrounding is, let's say, 35 degrees C. Now you can see that this difference is 7 degrees C. So it's in degrees C is not a very large difference compared to T naught, but you have to convert this to Kelvin. So T naught is 300 Kelvin. Okay. And the temperature of the surface is how much now? So 308 Kelvin. Okay. So the difference that is equal to 8 Kelvin. Now you can see that this is very small compared to T naught. Okay. But don't make the mistake of comparing the difference in degrees C, because that's not the case then. Okay. So if this happens, okay, then we can apply, then the net rate of heat loss, which we write as minus dq by dt net, which we write as E sigma into surface area into T to the power 4 minus T naught to the power 4. So in this net rate of heat loss, what we'll do is T naught will be a constant because it's the outside environmental temperature. Or atmospheric temperature. So we will assume that the atmospheric temperature is not really changing significantly as the temperature of the surface is changing. Okay, but T is equal to T naught plus delta T, where delta T is very small compared to T naught. So there is some scope for applying approximation over here. Okay, so let's see how that works. So minus dq by dt net. Now we can write T as T naught plus delta T, so that limit will come into play, that delta T is small compared to T naught. Okay. Further step, we can take T naught common from this whole bracket. So it will come as T naught to the power 4 outside, and this will become 1 plus delta T by T naught to the power 4 minus 1. So the moment we write this expression like this, so right now there's no difference. This expression is equivalent to this. It's just another way of writing it. But the moment we have written it like this, now because of this factor, you can see that we can apply binomial approximation. Okay, we can apply the binomial approximation that 1 plus delta T by T naught to the power 4 can be approximated as 1 plus 4 times delta T by T naught, because delta T by T naught is automatically small compared to 1. Okay. So just make a quick note of this up to here, or make sure you understand this up to here. Okay. And then we will take this further down. Okay. We'll substitute this whole bracket over here with the approximated value, and we will see, we'll get the statement of what is called Newton's law of cooling, that the rate of cooling is directly proportional to temperature difference. That means the rate at which the given surface is cooling down because it's at a higher temperature than the surrounding, that should be directly proportional to delta T. Is something that is not intuitive from Stephen's law, because according to Stephen's law, the rate at which heat loss is happening depends on T to the power 4 minus T naught to the power 4. So how can it be directly proportional to delta T? But we can see that that happens in the special case when the temperature difference is negligible compared to the temperature of the surrounding. So the binomial approximation method becomes applicable. Okay, so now as we come to this step, so we're seeing that the net rate of heat loss. Next step, we will put in this value. We will put in this value here will be substituted for this thing. Okay. So substituting that, we have minus dq by dt net will become approximately E sigma into surface area into T naught to the power 4, 1 plus 4 delta T by T naught minus 1. So next this one cancels out. So we get that the net rate of heat loss is equal to E sigma S into, now bring this outside. Okay, so this will become 4 T naught cube into delta T. Okay. Or we can say that the net rate of loss of heat is equal to some constant. Remember, the environmental temperature is also constant. So this constant into delta T, which is T minus T naught. So from this, we can see that this rate is directly proportional to the temperature difference, but provided delta T is small compared to T naught only. Because after all, this is an approximation. And this approximation is valid for this condition. Okay. So now we are coming very close to the statement of Newton's law of cooling. Okay. Now you have to understand one thing. Newton's law of cooling was an observational formula or an observational law that was given by observing the temperature of a cooling object, okay, as it is left in an open environment whose temperature is less than the surface temperature. So it was purely an empirical law that came from experimental observation, and it came long time before Stephen's law of radiation had been established. Okay, so Newton's law of cooling was a purely experimental law based on that limitation that delta T is very small compared to T naught, and based on observation of real life experimentation. Whereas Stephen's law of radiation justifies that experimental result, albeit under the condition of that special case that delta T is not less compared to T naught. If that condition is not satisfied, then this will not be the case. Then the rate of cooling will be proportional to T to the power 4 minus T naught to the power 4, rather than proportional to T minus T naught. Okay. So what we will study as Newton's law of cooling is, you can see it is just like a special case of the application of Stephen-Boltzmann law of radiation. It's not really something separate from the theory of radiation. It's named separately because it was a law that was developed a long time before Stephen-Boltzmann law of radiation. It was an experimental law, but it's completely justified by the Stephen's law. Okay, so now the final step here, we can see that if the given body, okay, which has surface area of S, right? Emissivity of E, okay, at temperature, at surface temperature T. Suppose if that given body has a heat capacity C, okay. Now C will be equal to mass into specific heat capacity if it is a solid body with mass M and uniform specific heat capacity. Small s. Okay. So in that case, dq is equal to C into dt. Okay. Or dq is equal to ms dt if this situation is considered. Okay. If this situation is considered. So the left hand side, the net rate of heat loss becomes minus of C, heat capacity, into the rate of cooling, the rate at which the temperature is dropping, and that is proportional to T minus T naught. So then basically we can say that minus dt by dt is equal to, or is proportional to, the temperature difference. And this exactly, this equation that we are writing here, this proportionality that we are writing here, this is in fact the statement of Newton's law of cooling. Okay. So Newton's law of cooling in the original experimental statement just gave the proportionality, not the constant. The constant had to be determined from experimentation. But if we derive Newton's law of cooling by using the approximation on the Stephen's law of radiation, you can see that we can even show how much the constant of proportionality is in terms of the properties of the body. Okay. So this is the statement of Newton's law of cooling. Provided, of course, for the condition that delta T, which is the temperature difference, should be very small compared to the temperature of the surrounding. Okay. Or basically from that you can say delta T by T naught should be very small compared to 1. So provided that condition is satisfied, Newton's law of cooling says that the rate of cooling, that is the traditional statement, is proportionate to, what we mean by proportionate is directly proportionate, okay, the temperature difference with respect to the surrounding. Okay. Now here you can also see that the constant of proportionality is in fact equal to E sigma into surface area divided by heat capacity into 4 into T naught cube, because you have all these things. Oh, just a minute, I have made a mistake here. There should be T naught cube. Okay, just make a correction here. If you're writing down the notes, please be alert and make this correction, because see, when you do this, there's a T naught cube here because of this in the denominator and this here. So please make a correction here. There should be T naught cube in this place. Okay. Anyway, so this is the constant of proportionality. Okay, where C is the heat capacity of the body. So C might become equal to M into S if it's a solid body of mass M and uniform specific heat capacity small s. So again, at JEE advanced level, when we are solving this type of application of Newton's law of cooling, now, we might be required to relate the constant of proportionality in Newton's law of cooling with the constant of proportionality that we get by applying the approximation of Stephen-Boltzmann law. Okay. So this is from Stephen's law of radiation. But using the approximation for the condition that delta T is small compared to T naught. Okay, if this condition is not satisfied, the equation will be slightly different. Instead of that 4 T naught cube into that factor, you will have T to the power 4 minus T naught to the power 4. So in general, we cannot say rate of cooling is proportional to temperature difference. Yes, Aman, thanks for pointing that down. I had not seen your message earlier. This exponent of T naught should be 3 and not 4. Okay. So now there are some different types of questions related to Newton's law of cooling, which we have to know how to solve. So this form in which we have written the equation that the rate of cooling is directly proportional to the temperature difference. This is the formula of Newton's law of cooling in the differential equation form, that is giving us the rate of cooling. Okay. Now this can also be integrated to get the relation between temperature and time rather than the relation between temperature difference with respect to rate of cooling. We can also get the relation of temperature as a function of time itself. Okay.
Sir, I didn't understand that equation minus dq by dt net is equal to minus c dt by dt.
Because see in that, okay, I got it. Okay, so you have understood this equation. Huh? This one I've written above here. This is clear.
Yes, sir.
Okay, now the main thing is how we have got this. No. Okay, so the thing is in time dt, in a small time dt, if the heat exchange of the body with respect to the surrounding is minus dq, then what temperature difference this heat exchange will create? What temperature change it will create? So for that we have that relation, that delta Q is equal to ms delta T for an isotropic material, or heat capacity into delta T. So understood this now? No? So
yes,
minus
sir.
dq is heat capacity into whatever temperature change that is happening. So that temperature change will be a negative quantity, so we'll write it as minus CdT. So removing dq amount of heat will result in a temperature drop of dt, or the temperature change will be minus dt. So we can replace that dq in the numerator with minus dq in the numerator can be replaced with minus cdt. ठीक है ना? Clear now ना बेटा?
Yes, sir.
Okay. So just make a quick note of this, then we'll look at questions based on this. Okay, so now let's see some typical application type of questions. So Newton's law of cooling is that rate of cooling is directly proportional to temperature difference. Okay. provided temperature difference is small. So specifically here we say that the rate at which the temperature of the surface is dropping should be directly proportional to T minus T naught. Okay, provided T minus T naught is small compared to T naught. Okay, so that is the meaning of this. Okay, so one type of direct application question is that the surface of a body at, let's say, 32 degrees C, okay, drops to 31.98 degrees C in 10 seconds in an environment at temperature equal to 27 degrees C. Okay. At a later time, its temperature is, let's say, 29 degrees C. Okay. How much will it drop to in the next 10 seconds? Okay. So go through the question. You might find it a little abstract. I'll explain it. Okay. That how exactly we'll use Newton's law of cooling. I'm just telling you something here, and I'll explain how that's happening. We will not have to use integration in this. Okay. In this particular example, we will not have to use integration, because what's happening that according to the information given, in 10 seconds, the temperature is dropping from 32 to 31.98. So the change in temperature is a very small change. So we can equate the average rate of change with the instantaneous rate of change. Even though it seems like 10 seconds is a very long time, so how can we equate instantaneous rate of change for a dt of 10 seconds? But in the context of how slowly this body is cooling down, you'll realize that 10 seconds is a very short amount of time, because overall it's going to take at least a few minutes to cool down. Okay. So just what I said, use that as a hint and try to understand how we'll solve this. Okay, I will discuss in detail. Okay, the hint is we will not have to use integration. Not hint, but hint. No need to integrate. Okay, because delta T of 32 minus 31.98, it's a very small change. Okay, so therefore, delta T by delta T can be approximated as dt by dt for okay, so it again comes back to what we mean by infinite versus infinitesimal in a physics context. Okay, anything that even seems pretty large, like a time interval of 10 seconds. If we talk about instantaneous velocity of a moving object, for example, we will never take delta t equal to 10 seconds as an infinitesimal interval of time. Not unless we are talking about a journey which takes days or something like that. So we can afford to take 10 seconds as a very small interval of time. But in this context, we will see that the cooling is happening so slowly, because in 10 seconds, the temperature is dropping by only 0.02 degrees Kelvin, or 0.02 Kelvin, where the surrounding temperature itself is 300 Kelvin. So in the context of the rate of cooling, it's a very small change. So that's the important thing to understand here. Okay, so let's try and understand how we'll do this now. So if we take this statement into account, that minus of the rate is equal to some constant into t minus t naught. Okay, this. Now this instantaneous rate can be approximated as an average rate for small changes. Okay, so 32 degrees C to 31.98 degrees C in 10 seconds. That is a temperature change of minus 0.02 Kelvin per 10 seconds. So that we will approximate as this, because this is a small change. Okay. That delta T of 10 degrees C is very small. So according to that, when we substitute this information, in this equation, we get that 0.02 upon 10 is equal to this constant, whatever it is, into 305 minus 300. Okay. So that constant is actually 0.002 divided by 5, or it is 0.0004 second inverse. This constant in this equation. Okay. In this particular equation, the value of this constant now we have determined from the given data, because this was the given data. Okay. Now we apply it to the second situation. Now additionally, the temperature goes from 20, how much was it? 27 degrees C, right? No, sorry, 29 degrees C to 29 minus some delta T in a time of 10 seconds. So we have to find this delta T prime. Okay. So at this point of time, the temperature of the surface, let's say T prime, is 302 Kelvin. So the rate of cooling, it should be equal to this constant into T minus T naught. That rate of cooling will be this. Minus sign will not be there. So this should be equal to that same constant into T prime minus T naught. Now this constant was how much? It was 4 into 10 raised power minus 4 into this temperature difference was 2 kelvins. Okay. So what will happen is, it will go from 29 degrees C to 28.992 degrees C in 10-second interval from the instant when temperature was 29 degrees C. So at some instant it's later 29 degrees C. So at a time of 10 seconds after that instant, it would have dropped to only 28.992. Yeah, I mean, we don't need to do, that's correct, Aditya, that's correct. We don't need to express in so many, different words and all that. We can just do a comparison. Okay. What we can do is, we can say that, okay, initially, let's say the temperature of the surface was 32 degrees C. Temperature of the surrounding was 27 degrees C. So the rate of cooling was equal to some constant into T1 minus T0. So 0.02 was it divided by 10 in Kelvin per second was equal to this constant into 2 Kelvin. Oh, sorry, 5 Kelvin. So let's say this is my equation 1. Okay, so this whole thing is my equation 1. I just need to compare this with the second information. After some time, the temperature of the surface has become 29 degrees C. Temperature of the surrounding, of course, is still 27 degrees C. So at this point of time, the rate of cooling is equal to that same constant into T2 minus T1. So whatever this new temperature change divided by this is equal to that same constant into, now this temperature difference is 2 kelvins. So let's say this is my equation 2. Now just divide the two equations. Do equation 2 divided by equation 1. So you will see that delta T divided by, or minus of delta T divided by 0.02 is equal to 2 divided by 5. So delta T should be minus of 2 by 5 of 0.02. So that is 0.8, 0.4 into 0.0. So it's minus of 0.008. Okay. So the temperature should drop by 0.008 degrees C or Kelvin in the next 10 seconds from 29 degrees C onwards. So this is the easiest way to execute the problem and visualize it also. So delta T is the change in temperature in the next delta T equal to 10 seconds. So Aditya, this was the point you were making, right? Aditya Vansali, we can just form these two equations and divide, right?
Yes.
Okay. Okay, now next we will look at the actual variation of temperature over a long period of time, how it happens. But before that, we will just understand one more thing about the same problem. In the above example, okay, if we want to calculate, the total time taken for the surface temperature to drop from the two given values from T1 equal to this thing 32 degrees C to T2 equal to 29 degrees C. Okay, we will have to integrate the rate equation. Okay, because this T1 minus T2 is a change of how much? It is a change of 3 Kelvin. Okay, and if you see T1 minus T0 or T2 minus T0 with respect to the surrounding, the temperature difference was 5 Kelvin initially, 2 Kelvin at this stage. So this is a large change. This is a large drop in temperature. It is not like a small drop from 32 to 29.98 or from 29 to 28.992. It's not like that. Here the change is very small. Okay, so these are very small changes, but this is a large drop. So for this kind of situation, what we have to do is we have to take this relation that at some instant of time, the temperature of the surface is T. Okay, so at T equal to T plus dt, the temperature of the surface becomes T minus dt. So during this time, this rate is equal to that constant into T minus T0. So okay, so now this has to be integrated. This has to be integrated from whatever time T1 when the temperature was capital T1 to whatever time T2 when the temperature becomes whatever T2. So this equation will give us the time for the temperature to drop from T1 equal to 32 degrees C to T2 equal to 29 degrees C. So that is what we mean by saying that we will have to integrate the rate of change equation. Okay. So just make a rough note of this, and we will actually develop this like an equation. Instead of just solving for this particular question, we will develop this as a general equation. And through that general equation, we'll see something interesting about the behavior, about how the temperature of a surface drops with respect to its surrounding. Okay, so what we'll do is now we'll solve this differential equation not only for this particular question where we are finding out the time taken for the temperature to drop from 29, I mean from 32 to 29, but as a general equation. Okay. So the second form of Newton's law of cooling, that is when we integrate the rate law to get the temperature as a function of time. So this is some C into T minus T naught. Now don't confuse this C with the heat capacity. Okay, here C is just the constant of proportionality. For the rate change. Okay. If you relate this with Stephen's law, okay, under the condition that T minus T naught is very small compared to T naught, okay, then you get that constant of proportionality as actually equal to 4 times E sigma S into T naught to the power 3 divided by, let's say, C prime, where C prime is the heat capacity. C prime is equal to MS for an isotropic bond. So it has a uniform specific heat capacity. So that thing. Okay. So now in this, so this is Newton's law in differential form, in differential equation form. Okay. Now if at T equal to 0, the temperature of the surface was T initial. Okay. Then by integrating the above relation, above differential equation, we can express the instantaneous temperature T as a function of time T. Okay. Of course, by temperature we mean surface temperature. Okay. So in our particular example, what was happening is that the surrounding temperature was 300 Kelvin. The initial temperature of the surface was equal to 305 Kelvin at T equal to 0. Now we want to find the temperature at T equal to T. Okay, let's say that. And additionally, we had also seen that the constant C was equal to 0.002 second inverse, because the temperature was dropping by 0.02 degrees C at or in 10 seconds initially. So because this data was given, so the constant of proportionality had come out to be this. Okay, so now let us see how we will integrate this relation. So we will get this. Okay, so I can just transfer the negative sign on that side and now integrate it like this, taking the constant outside. So at T equal to 0, the temperature of the surface was the initial temperature, and at T equal to T, the temperature is the instantaneous temperature, capital T. Okay. So as you know, here T naught is a constant. So integrating with respect to capital T, we'll get natural log. Okay, but with the limits that capital T is going from the initial value to the instantaneous value. On the other side, we have minus Ct, but for small t, the limits are that T is going from 0 to instantaneous time T. So substitute the limits. We have this, and substitute here we have this. So we get the relation that natural log of t minus t naught divided by t initial minus t naught is equal to minus ct. Or taking exponential on both sides, we get this is equal to e raised power minus ct. So now we get that t is equal to t naught plus t initial minus t naught into e raised power minus ct. This is the relation that we were after. The temperature as a function of time. If we put this data into it, we will get that T is equal to the surrounding temperature 300 plus the temperature difference initially. So the initial temperature difference is 5 Kelvin. So plus 5 into e raised power minus 0.002 T, where T should be substituted in seconds. So T is in Kelvin. So this is what this would become if we take this data over here. Okay, so I'm just going to minimize this a little, but just go through the steps. Okay, and the thing is, like, at the exam level, you will not get that much time to, I'm not saying you have to memorize this formula, but you should be very clear with the steps so that you can come from the rate equation to the instantaneous equation very fast. You should not have to think a lot about how to do these steps and all. It should be pretty obvious. So just practice this derivation a couple of times. In any case, this kind of integration is going to be very useful and important in physics in various chapters. When we get that logarithmic form, and by taking anti-log on both sides, we get something as an exponential function. So here we will see that when we plot the graph, we'll understand that the temperature of the surface is decaying exponentially from the initial value, let's say 305 Kelvin. It is going towards the surrounding temperature as of 300 Kelvin as time progresses. So Marup, did you need the part above this or from here onwards? Do you need to see the section above this or? Okay, okay. So I'll just take you to the above section once, then we'll come back to this. Okay, so let's move on to the part below. Okay, so let's understand this in terms of a graphical relation also. So if we are looking at the temperature of the surface versus time graph, see that this relation, that instantaneous temperature is surrounding temperature plus initial temperature minus surrounding temperature into e raised power minus that constant into t. So this basically means that, first of all, from this you can see that temperature is decreasing with time. Okay, because that e raised power minus ct factor is a decreasing function of time. If you plot y is equal to e raised power minus ct, that graph will be of this type. Y tends to 0 as t tends to infinity. So that's the first thing. So according to that, you can see that t will be equal to ti at t equal to 0, because this factor will be unity. Okay. And t will tend to become equal to t naught as t tends to infinity. Okay. So that is why if this is my surrounding temperature T naught, which is let's say 300 Kelvin, and this is the initial temperature Ti, which was in that case 305 Kelvin. Okay. Then the graph of temperature versus time will be exponentially decaying from this initial value as time progresses, but it will literally take infinite amount of time. So by infinite we mean a very long, very large amount of time it will take to approach this. Okay. So it's an exponentially decaying curve from T equal to Ti to T tending to the surrounding temperature. So for example, we want to find T when the temperature becomes 302 Kelvin, given that the initial temperature was 305 Kelvin. The surrounding temperature was 300 Kelvin, and the constant was 0.002 second inverse. Okay, so all we have to do is we have to use this equation that T is equal to this quantity. So in this, substitute this information. Substitute this here. So we'll get 302 is equal to 300 plus 5 into e raised power minus of 0.002 t, where t is in seconds. So now we have to solve this for time. Okay, so now let's see how we'll solve this for time. So it's just a bit of trick of solving for logarithms. So 2 is equal to 5 e raised power minus 0.002t. Okay, so we can see that e raised power minus 0.000t 2t is equal to 2 by 5. Or we can just reverse this and say that e raised power 0.002t. I think I've got an extra zero in between here. Yeah, this should be equal to 5 by 2. Now take exponential, or take log on both sides rather. So this is ln of 5 by 2, which you can write as 2.303 times log of 5 by 2, which you can write as 2.303 log of 10 by 4. So log 10 minus log 4. This is 0.002t, right? So t will become 10 raised power 3 by 2 into 2.303 into 1 minus 2 into 0.3. So this much in seconds. Okay, because log 2 is, so these are useful values to remember. Log 3 is, okay, log 5 you can always relate as log 10 minus log 2. Like this. Okay, so these are some common values of log. It's worthwhile remembering for these type of calculations. Into this will become 0.6 or 0.4. So these many seconds. Okay, so you can see that the amount of time it takes is quite large. Okay, so we could not have used the rate of change thing. So just to give you a perspective, if this is our temperature versus time graph, okay, so that graph is decaying, like let's say something like this, from t initial to t naught. Okay, now earlier what we had taken was this small interval. So for this we could treat the secant line as the tangent line. Okay, or as the temperature was going from 302 Kelvin to something very close to that. Sorry, 302 Kelvin here. This was 305 Kelvin. So you can treat that kind of change. Okay, but now between these 2 points, where the temperature is 305 and 302, we cannot take secant line equal to tangent line. You understanding? No? Okay, so this time corresponds to this temperature drop. If from 305 to 302. Yeah, so Aditya has done the calculation. So have others. Aman has also done the calculation. Nikita, you also done. So you can see that it's in minutes. It's approximately 7.6 minutes. So that is why we were able to treat that 10-second interval as a differential element or as a differential time difference. Because the overall range of time in this system is several minutes. Okay. So anyhow, I hope this is clear. Okay. let's bring today's session to an end with this, and next time we will look at some more examples of application of Newton's law of cooling or application of Stephen Boltzmann law of radiation, but with approximation, binomial approximation kind of thing that we use for Newton's law of cooling. And we will look at the final theory part, which is about how the radiation is the emission from a black body. That radiation is distributed over electromagnetic spectrum. So we will see the relationship between the spectral emissive power and wavelength. Okay, so that's a small theoretical principle, law called the Wien's displacement law. So we'll understand that because it's a significant law in the evolution of thermodynamics, especially radiation. Okay, though for us it will be just a small formula, so nothing really significant. With that, we will complete heat and thermodynamics, and next section we will be starting will be fluid mechanics and properties of matter. Right. So the next chapter we'll be doing will be properties of substances, which will include fluid mechanics and properties of solids like elasticity, and then properties of fluids like surface tension and elasticity. So that will be the next section of physics for us. Okay, so that's it for today. We will wish you all the best.